All right, let's get started. So good morning, everyone. My name is Nathan Marz, and today I am presenting about Storm. So first I want to start off with some basic information about the project. Storm was open sourced on September 19th of last year. The implementation is only 15,000 lines of code. About half of that is Java, and half of that is Clojure. So it's a pretty small code base, but as you're about to see, it packs quite a punch. Storm is already used by over 25 companies. And Storm has a lot of people watching it on GitHub. It's actually the most watched JVM project on GitHub. And it has a very active mailing list and very active community. So before I get into Storm, I want to talk about how we did real-time computation before we had Storm. And the purpose of this is to see what are some of the intricacies of real-time computation that motivated us to build a whole new system for this. Now, the way we built systems before Storm was using the queues and workers paradigm. We certainly were not the first ones to try this. A lot of people build real-time systems this way. So our architecture before Storm looked like this. It was a little bit simplified from what we actually had. But we were building an application that did analytics on Twitter data. So we had the Twitter firehose, and we would take the Twitter firehose and put it onto a cluster of queues. And then we had a first set of workers that would take each tweet and put it into our schema and append it to Hadoop. And then we had a second set of workers that would look at all the URLs being tweeted and then update various statistics on those URLs by incrementing counters in Cassandra. So we did things like number of tweets per URL over time, or impressions per URL over time, and things like that. Now, one of the interesting things about this architecture is that we actually had the constraint that the same URL always had to be processed by the same worker. Now, the reason we had this constraint is because Cassandra is not transactional, and at the time it didn't have atomic counters. So if you had multiple workers all updating the same URL, you'd have a race condition, and you'd lose data. You'd lose counts because they would trample on each other. But by making sure the same URL is always updated by the same worker, you prevent the race condition, and the system works. Now, the way we actually implemented this is that we'd actually have the first set of workers choose the worker to send the URL to by taking the hash mod of the URL. So the hash of the URL modded by the number of workers to select the consuming worker. Right? And this has the effect of the same URL always going to the same worker, but it still distributes the URLs evenly across the workers. Now you can start to see where there are problems with this architecture when you look at what you need to do when you need to scale this system. So let's say that we need more workers to be updating Cassandra. Okay, so to add a worker to that set of workers, you have to first of all deploy that new worker, and you have to deploy a new queue for that worker. Probably a logical queue, not necessarily a physical queue. But then where it gets kind of nasty is that you actually have to reconfigure and redeploy the first set of workers, because now that there are more consuming workers, the hash mod algorithm needs to be updated to know, oh, there are more workers, so we're going to distribute the URLs differently. So you can kind of see there's these cascading dependencies throughout the architecture. Scaling one piece requires changing other pieces in the system. So scaling a system like this was pretty painful. Another big problem is that the fault tolerance of systems like this is pretty poor. There's things you can do by having more workers for failover and things like that, but it all ends up being pretty tedious and doesn't really work that well. And kind of the worst problem with this architecture is that coding it is really tedious. You spend most of your time in your code thinking about where am I going to send messages to, where do I read messages from, how am I going to serialize messages. When you actually get to the business logic you care about, it ends up being a relatively small percentage of your code base. So we looked at this system and other real-time computation systems, other real-time problems we had, and we came up with this list of 6 things that we really want from a good real-time system. So the first is that a real-time system must guarantee that data will be processed. This is just too important for too many applications. The second is it needs to be horizontally scalable, but not just horizontally scalable, easily horizontally scalable. So just add a few nodes, tweak a few knobs, and have everything just work. The third is it needs to be fully fault tolerant, so if there's any errors during processing or you lose a node, the system should self-heal and keep on running. The fourth property is an interesting one. We said we want to get rid of all those intermediate message brokers. So if you look at our architecture from before, you can see that between every set of workers, you have this set of intermediate message queues. Now the problem with these intermediate brokers is that, well, first of all, they're very complex. There's a major moving part pervasive throughout the whole system. And second of all, they're slow. Right? Instead of sending messages directly from your producers to your consumers, you have to go through a third party. And even worse, that third party has to persist that message to disk. But the reason you have those intermediate message brokers to begin with is for that guaranteed data processing property. The idea is that if a worker fails to process a message, it can just replay the message off the queue it got it from and only take the message off the queue once it successfully processes the message. So if we get rid of intermediate message brokers, we need a whole new strategy to guarantee data processing. The fifth property we want is a higher level abstraction than message passing. So low level message passing is clearly the wrong level of abstraction for this. And we want things like partitioning and serialization and routing all handled for us. And last property is that a real-time computation system needs to be extremely robust. So as a point of comparison, let me use Hadoop. Who here has used Hadoop before? OK, a fair amount of people. So anyone who's used Hadoop can tell you horror stories of some crazy stack trace you get, and the whole cluster stops working, and you have to spend a few hours or sometimes longer to dig into the implementation of Hadoop and figure out that there's some obscure configuration parameter that you need to tweak just to get the thing running again. Certainly, this has happened to me dozens of times in my usage of Hadoop over the past 3 or 4 years. But in some ways, that's OK for Hadoop, because Hadoop is a high latency system. So if you take a few hours of downtime, you're still high latency. Now, with a real-time system, if you take a few hours of downtime, you're no longer real-time. So the robustness requirements are much, much higher. So Storm, of course, satisfies all these properties. I wouldn't have mentioned them if it didn't. So Storm has 3 broad sets of use cases. These are by no means all-inclusive, but it's a good way to think about the various kinds of problems that Storm can be applied to. So the first I call stream processing. So the idea here is that you process a stream, and maybe you update your databases, and then you just forget about the messages. The second one is called distributed RPC. So this is a completely different use case. The idea here is that you have some function that's really intense to compute. It's too intense for one machine, and you need to compute it on the fly. So what you can do is you can actually implement that function on top of Storm, let Storm parallelize the function for you, and then you use Storm as an RPC mechanism. So I'll have a lot more to say about this later in the talk. The third use case I call continuous computation. So the idea here is that you have some function which you want to continuously know the results to. So an example of this is, let's say, computing trending topics off of the Twitter fire hose. So a Storm cluster looks like this. There's 3 sets of nodes in a Storm cluster. The first is called Nimbus. It's the master node, and it plays a role similar to the Hadoop job tracker. So Nimbus is where you upload your computations for execution. Nimbus will distribute your code across the cluster, and then launch workers across the cluster to execute your computation. And then Nimbus will go ahead and monitor your computation and restart any workers and move them around if anything goes wrong. In the middle, you have a Zookeeper cluster. So Zookeeper is actually a different project. It's an Apache project. It's basically built for doing cluster coordination, and that's exactly what Storm uses it for. So the third set of nodes are the worker nodes, and every worker node runs a daemon called the supervisor, and the supervisor communicates with Nimbus through Zookeeper to determine what should be running on that machine, and then the supervisor will start and stop workers as necessary, as dictated by Nimbus. So let's say you have a computation to run. So computations in Storm are called topologies. So here's how you start it. So Storm has a command line client called Storm, and you'd say Storm jar, give it your jar containing your code and dependencies, and then give it the class to run and the arguments to that class. And this command will go ahead and upload your jar to the cluster and then tell Nimbus to start the topology. So topologies actually run forever, but if you ever want to kill a topology, you'd say Storm kill and then the name of the topology. Okay, so let's dig into the concepts of Storm. So Storm has 4 main concepts: streams, spouts, bolts, and topologies. So streams are the core abstraction in Storm. When you're using Storm, you're manipulating these infinite streams of data. And a stream is just an unbounded sequence of tuples, and a tuple is just a named list of values. You can put any type you want in tuples. If you give it an object that Storm doesn't know about, you provide a custom serializer, but that's all very easy to implement. The next abstraction is called spouts. So spouts are sources of streams in a computation. So a spout might do something like read from a Kestrel server and emit those messages as a stream. Or maybe it'll connect directly to the Twitter streaming API and emit those tweets as a stream. Then you have bolts. Bolts process any number of input streams and then produce any number of new output streams. So most of your logic in your application goes into these bolts. So bolts can do anything from run functions, do filtering, do streaming aggregations, do streaming joins, talk to databases, you name it, your logic tends to go in these bolts. So finally, the top-level abstraction in Storm is called a topology, and a topology is just a network of spouts and bolts, where every edge in the network indicates a bolt subscribing to the output stream of some other spout or bolt. One of the key things about Storm is that spouts and bolts are inherently parallel. So they execute as many tasks across the cluster. So like in this diagram, the spout on the left has 2 tasks, the bolt on the top has 3 tasks, and the bolt on the right and bottom each have 2 tasks. And the tasks actually communicate directly to one another, passing messages. So this is like a logical view to look at what a topology looks at. Like a physical view for how it's actually executing might look like this, where here we have 3 worker nodes, and each node has some number of workers running on it. A worker is an actual JVM process. And each worker process has some number of tasks running within it. So like for the spout, let's say the spout is S, you can see it has a task on the bottom left node and also on the top node, right? And then bolt B1 has tasks on all the nodes, and B2 has tasks also on all the nodes, right? And then these workers communicate directly to one another, passing messages. Okay, so the fact that spouts and bolts are inherently parallel brings up the question of when a task emits a tuple, to which consuming task should it send the tuple, right? So here you have a bolt with 3 tasks sending messages to a bolt with 2 tasks. When a task on the left emits a message, which of the 2 tasks on the right does it choose to send the message to? So you answer this question in Storm by providing what's called a stream grouping. And a stream grouping just says how to partition the stream of messages. So the simplest kind of grouping is called a shuffle grouping. So in this case, it actually picks a random task to send the message to. So this has the effect of evenly distributing the load of processing the messages. A more interesting kind of grouping is called a fields grouping. So here, it chooses the target task by doing mod hashing on a subset of the tuple fields, right? So this should sound awfully familiar to what I was talking about in the beginning of my talk, but now it's done at a higher level of abstraction. Another kind of grouping is called an all grouping. So in this case, you actually replicate the tuple to all tasks. Obviously, this can seriously blow up the size of the stream, so it should be used with care. Another kind of grouping is called a global grouping. So here you pick the target task by picking the task with the lowest ID. So this has the effect of all tuples going to the same consuming task. And there's a few other kinds of groupings, but they're a bit beyond the scope of this talk. So if you actually look at the topology diagram again, it actually looks something like this, where every edge is annotated with the kind of stream grouping used. All right, so let's dig into the code of how you would use Storm. So I'm going to show an example here of implementing streaming word count on top of Storm. So the idea is that as input, we have a stream of sentences, and we want to output a stream of word counts, where we just emit a new count for the word every time we see that word again. So first, you start by creating this topology builder object. Topology builder just provides a very nice API for constructing topologies in Java. So now let's create our first spout. So here we say builder set spout, and then you give the spout an ID. So here we name it spout. And then the implementation of the spout is this Kestrel spout object. And here we're just saying, let's read messages from the sentence queue off of that host and port. And then we give this spout a parallelism of 5. So that just means there will be 5 tasks spawned across the cluster, all hitting that kestrel queue, receiving messages, and then emitting them into the topology. Okay, so now let's create our first bolt. So this bolt is called split sentence, and it will take a stream of sentences and emit a stream of words. So this bolt, we give it an ID of split. The implementation is split sentence, which we'll look at in a second. We give this bolt a parallelism of 8. So we're going to spread the load of splitting the sentences across 8 tasks across the cluster. And then we say this bolt reads its input from the spout component using a shuffle grouping. So the spout component was what we just defined here, the kestrel spout that's emitting the sentences. And this says, I want the messages, I want to read that entire stream, and I want the messages sent to me partitioned with a shuffle grouping. So as you can see here, it's the consumer who decides what data it receives and how it gets grouped, which when you think about it is really the right way to think about it. So now the last bolt in this topology is the word count bolt. So this bolt takes in a stream of words and emits a stream of word counts. So we give this bolt an ID of count. The implementation is word count, which again we'll look at in a second. And we give this bolt a parallelism of 12. And then in this bolt we say we want to read from the split component using a fields grouping on the word field. So you might be wondering, okay, why are you doing a fields grouping here? Why not do a shuffle grouping like you did before? Well, the problem with a shuffle grouping is that if we did that, then the same word may actually go to different tasks in the word count bolt. And so each of those tasks would have an incomplete view of the number of times that word has appeared, and so wouldn't be able to emit the right count. By doing a fields grouping, the same word always goes to the same task, and then that task has seen the whole history of that word, and then it can emit the right count. Okay, so here's the implementation of split sentence. So I chose to implement this in Python just to illustrate Storm's multi-language capabilities. So first at the top, you have a small wrapper class, which just says, I'm implemented in Python, and here's the file that implements me. And then at the bottom is the implementation, and it's really simple. Every time the bolt receives a tuple, that process method is called. And then what it does is it takes the first value of the tuple, which is the sentence, and it splits it on white space. And then for each of those words, it emits it as a one tuple. So here's the implementation of word count. So the way this works is it actually keeps the word counts in an in-memory hash map. I just did this for demonstration purposes. You could, of course, use a database or something for this as well. And then every time it receives a tuple, it grabs the word from the tuple, updates the word count in its map, and then emits the new word count. OK, so that's it for defining the topology. So let's say you now wanted to run this on a cluster. So here's how you would do that. So first you create a configuration for your topology. So here we say we want to set topology workers to 10. So that means there will be 10 physical JVM processes spawned across the cluster, and then all the tasks for your topology will be evenly spread across those workers. And then you say storm submitter submit topology. You give your topology a name, you give it the configuration, and then you give it your topology definition. So this will go ahead and upload your code to the cluster, and then tell Nimbus, OK, spawn this topology. Storm also has a local mode where you can actually simulate an entire Storm cluster in process and run topologies on it. This is super useful for development, testing, and debugging. So to run in local mode, it looks very, very similar to running on an actual cluster. So you say, what you do is you create this local cluster object, which simulates a Storm cluster in process. And you submit to it the exact same way you submit to an actual cluster. So here we set in the configuration topology debug to true. So this has the effect of logging to console every time a message is emitted. So this is, of course, very useful for debugging. OK, cool. So let me do a quick demo of Storm running. OK, so what I'm going to show here is the word count topology just running locally. It's the exact same code I showed you. The only difference is that rather than use a kestrel spout, I'm using this random sentence spout, which just generates random sentences all in memory. But let me run this here. Okay, so here you can see it running. I have it set to run for 10 seconds and then shut itself down. Okay, so it finished. And if you actually look at what it was doing, so let me find a good example. Okay, so here you can see the sentence spout emitted some sentences, Snow White and the Seven Dwarves, and an apple a day keeps the doctor away. And then you can see one of the word splitter tasks picked up that first sentence and starts splitting it, and another one picked up the other sentence and started splitting that. And then interleaved with that is the word count bolts picking up the words and emitting the new counts. And you can see all the processing is interleaved because everything's happening in parallel and everything is asynchronous. And just to show you what a spout looks like, so the random sentence spout is right here. And the way a spout works is it just has this next tuple method that you implement, and then here you emit a new tuple into the topology. So here you can see it just has these 5 sentences. Every 100 milliseconds, it picks a random one and emits it into the topology. So the code is really, really straightforward. All right, so now I want to talk more about distributed RPC, which I'll just refer to as DRPC from now on. So the idea behind DRPC is that you have some function that you want to execute on the fly, but it's too intense for a single machine, so you want to parallelize it across a storm cluster. So the data flow for DRPC looks like this. So you're on the left, and you have some function you want to execute, and you have some arguments to that function. So there's a server called the DRPC server, and Storm comes with an implementation of this. So you tell the DRPC server, here's the function I want to execute, and here are the arguments. So the DRPC server can actually act as the source for a spout for topology. And the DRPC server emits a stream of function invocations. So each function invocation is a tuple containing an ID for that request, the arguments for that request, which were provided by the user, and then the return info for that request. So the return info is just the host and port of the DRPC server. Right? The idea is that your DRPC server could be clustered, and you could have many of them. So then your topology, which implements the function, has a spout, which reads that stream and emits it into the topology. So your topology picks up that tuple and then does its thing to do the processing. And when it's finished, it sends the results to this special bolt, and it tells the bolt, for this request ID, here is the result. Here's what I computed. And then that bolt connects to the DRPC server and tells it, here's the result for this request ID. The DRPC server maps that result to the waiting client, unblocks the waiting client, and sends them back the result. So from the client's perspective, it looks just like regular RPC, but it's actually happening in parallel in the background. So let me give an example of a problem for which you really need something like DRPC. So the example I'm going to give is computing the reach of a URL on the fly. So the reach of a URL is the number of unique people exposed to a URL on Twitter. So to compute reach, what you have to do is take the URL, then get all the people who ever tweeted that URL. Then for each of those people, you have to get all of their followers. Right? So now you have potentially a massive set of followers. And then you have to take that huge set and distinct it, and then count the distinct set to get the reach. So just like to give like a number, if you did this with like a TechCrunch URL, this computation would involve thousands of database calls just to get the followers, and then tens of millions of follower records to sort through, distinct and count. So it's a really intense computation to compute on the fly. So we actually originally implemented reach just on a single machine, and for some of those hard URLs, it would literally take over a minute to run. So just awful performance. Then we implemented this on a storm cluster, and we got that latency down to 2 seconds. So the topology for reach is actually really straightforward. And here's what it looks like. So you have a spout, which emits function invocations. So it emits a stream containing request ID and URL. So the first bolt is called getTweeters. So it maps a stream containing request ID URL to a stream containing request ID tweeter ID. Right? So one URL maps to many tweeter ID tuples. So the next bolt is called getFollowers, and it maps a stream containing request ID tweeter ID to a stream containing request ID follower ID. And you can see getFollowers does a shuffle grouping on getTweeters to distribute the load of getting the followers. So now, for that request, you may have millions of follower tuples. So the next bolt is called partial distinct. So what it does is it does a fields grouping on the follower ID. So this has the effect of the same follower will go to the same partial distinct task. And what partial distinct does is wait until it's received all the follower tuples directed at that task for that request. And then what it does is it emits the unique count of those followers. So each partial distinct task emits one count for that request. Now the reason this works is that because we did a fields grouping on the follower ID, every partial distinct task receives a mutually independent subset of the followers. Right? So the same follower never goes to two different tasks. Right? So all that's left to do after partial distinct runs is take those partial counts and sum them together, and then you have your reach. And that's what count aggregator does. Does that algorithm make sense to people?
How do you know when you've gotten all the followers?
Great question. Let me answer that in the next slide. Okay, so here's what the actual code for this looks like. And it's pretty much exactly what I just described. Storm provides a higher level abstraction for DRPC. So this automates a lot of the stuff like setting up your spout and setting up the bolt that sends the messages back to the DRPC server. So that abstraction is called linear DRPC topology builder. And this also provides, let me get that. So this also provides that logic for determining when a task has received all the tuples directed at it. So then to define reach, you say add bolt get tweeters, add bolt get followers, which does a shuffle grouping, add bolt partial uniquer, which does a fields grouping on the ID and follower, and then count aggregator, which does a fields grouping on the ID. Doing a fields grouping on the ID is the same as doing a global grouping just for that request. Okay, so the implementation of get tweeters and get followers is really straightforward. Here's how partial uniquer works. So partial uniquer extends this batch bolt abstraction. And this is something that's provided by linear DRPC topology builder. And then you'll see how it works. So the idea is that a new instance of this bolt is created for every request. Right? And you can see in the prepare method, it's parameterized with the ID for the request. And then what you do is you keep the set of followers for this request in an in-memory set. And then every time you receive a new tuple, you just add that follower into the set. And then when this bolt has received all the tuples for the request, the finish batch method is called. And then you just emit the request ID and then the size of the set. Right? So linear DRPC topology builder handles all the logic to determine when to call finish batch. So you get a new instance of this for every bolt. Yeah. So if you actually want to know the mechanism for how it determines when to call finish batch, talk to me afterwards. But as you can see, for DRPC, you kind of have this first-class batch processing API for doing the processing. Okay, so let me actually show reach running. So here's the reach topology. So it's what I just showed you. Now, to demo this, I'm not going to be querying actual databases. I just have the databases mocked out in these in-memory hash maps. So here's like the tweeters DB. So this is just a map from URL to a list of tweeters. And here's the followers DB, which is a map from tweeter to list of followers. Okay, so what I have open here is the Clojure REPL. So Clojure is a dialect of Lisp that runs on the JVM. And I'm just going to be using this just to execute some Java code interactively. So the first thing I'm going to do is create a local DRPC server. So just like regular Storm, DRPC has a local mode. So now I have my DRPC server. And now I'm going to create my local Storm cluster. And so there you can just see the Storm cluster starting up. And now it's idle because nothing's running on it. So now I'm going to create that reach topology and submit it to the cluster. So it's submitting, and that's just the topology setting itself up. And now the topology is loaded up, and as you can see, it's not doing anything because I haven't made any function invocations on it. Okay, but now I can start doing some function invocations. So here I just call a method on the DRPC server, and I say, I want to execute on the DRPC server the reach function with this argument, right, this URL. Okay, and I press enter, and it comes back with the result 14. So you can see this looks exactly like normal RPC, but it's actually executing in the background on the Storm cluster. So if I give it a different URL, you get a different result. And then if I give it a URL it's never seen before, you get 0, just like you'd expect. All right. All right. So I said in the beginning of the talk that Storm gets rid of all those intermediate message brokers. So we need a whole new strategy for guaranteeing data processing. So let me talk a little bit about how that works. So the first thing you have to do is decide, what does it even mean to guarantee data processing? So the first thing you do is you look at, OK, what happens during the processing? What's actually going on in a topology? So what happens is that a spout emits a tuple, right? And those are kind of the root tuples in a topology. That's the initial streams. And that spout tuple goes to some set of bolts, and then they look at that tuple, and then that triggers them to emit some new tuples. Right? So they emit some tuples which are kind of dependent on that original tuple. And those tuples go to other bolts, and they emit new tuples based on those tuples, and those go to other bolts, and so on. So you end up with this tree of messages where each tuple was triggered or is dependent on the tuple before it. So for example, in word count, you have a sentence that comes off the spout, and then the word splitter bolt picks that up and emits a word, or emits a tuple for every word in that sentence. All right, and then the word count bolt picks up those tuples and emits a word count for each of those words. Right, so Storm calls this the tuple tree. What Storm says is that a spout tuple is not considered fully processed until all tuples in the tree have been completed. Until the whole tree has been exhausted and each individual node in the tree has been completed and is finished with. And if a tuple tree is not completed within a specified timeout, and this defaults to 30 seconds, you actually replay the tuple from the source. So you replay from the spout, and that will trigger the whole tuple tree to be regenerated. So replay always happens from the spout. So with this strategy, Storm provides an at least once guarantee on processing. So there's a little bit of work that you have to do to take advantage of this reliability, but it's pretty straightforward. The first thing is that you have to tell Storm whenever you're creating a new edge in that tuple tree. So here we say, so here's the implementation of the split sentence bolt in Java. So here you can see whenever it emits a new word, we put the sentence tuple as the first argument. So this is called anchoring, and this just creates an edge in the tuple tree. And then whenever you're finished with the tuple, you tell Storm, I'm done with this tuple, and you just act that input tuple. Right? And then Storm takes this and will construct the tuple tree in the background and track it and determine when is that tuple tree completed. So you might be wondering, OK, how does this really work? Right? Isn't it going to require like a lot of memory to keep track of the tuple tree for every spout tuple? Right? Because those things can get arbitrarily large. But it turns out you actually don't need to track the tree explicitly. Storm actually only uses about 20 bytes to track each tuple tree, regardless of how many pending tuples there are. So you could have 1 billion pending tuples, and Storm still only uses 20 bytes. It's a really, really efficient algorithm. It's fully distributed. And it's really the key to how Storm works and why Storm's able to get rid of those intermediate message brokers. If you're interested in the specifics of this algorithm, it's all documented on the wiki, or you can come talk to me afterwards. OK, so based on what I just described, so Storm provides an at least once guarantee of processing. Right? So you might be wondering, all right, so what if I want to do something like counting? Right? Is Storm completely useless for me? Right? Like, how do you do counting with an at least once delivery guarantee? Right? Like, aren't you going to overcount? So Storm provides a higher level abstraction called transactional topologies, which solve this problem. And they actually, transactional topologies are built on top of Storm's primitives of streams, spouts, bolts, and topologies. And on top of at least once message processing, it provides exactly once processing semantics. So just to be clear, it's not exactly once processing because that's impossible, right? If something fails, if like a node blows up, you have to replay something, but you can still get exactly once semantics. So do your computation in a way such that it was like you actually only processed every message one time. Okay, so transactional topologies work a little bit differently than normal topologies. So the idea is that rather than process just one tuple at a time, you process small batches of tuples at a time. And if anything in a batch ever fails, you replay the whole batch. Then you have your topology. Okay, so the processing of batches happens in two phases. There's the processing phase, and once you finish, if you successfully finish the processing phase, you move on to the commit phase. And so any number of your bolts can process in the commit phase, and those are called committers. So what transactional topologies provide that you don't have in regular topologies is a strong ordering. And in particular, it's a strong ordering on commits. So you're guaranteed that commits will be ordered based on how the batches were emitted. Now, if there's a failure, you might have to reprocess the batch and recommit. So it's kind of ordered commits, possibly with repeats. So for example, let's say you go to process batch 1, and let's say that commit fails for some reason. So you'll reprocess and recommit that batch, right? And then let's say that succeeds, then you move on to batch 2. Let's say that succeeds, you move on to batch 3. That succeeds, you move on to batch 4. And if that fails, you'll retry it again, and you just keep on going, right? So again, it's strongly ordered, potentially with repeats. If I go to commit batch 2, I will never, ever go back to commit batch 1 because I already succeeded. Okay, so on top of this strong ordering, you can get those exactly once semantics. So let me show how that works for something like counting. So here we have this idempotent counting bolt, and what it's going to do is it's going to update some count that you're storing in a database. So similar to that partial uniquer bolt I showed before, you get a new instance of this bolt for every transaction attempt. So Storm calls that the combination of the process and commit phases for a batch a transaction. Right, so the way this works is that whenever we receive a new tuple, we just increment a partial count that we just keep in memory, right? And then when it's time to commit, what we want to do is increment the count in the database by that partial count that we computed during the processing phase. Now the key thing, okay, so if you look on the top here, you can see this bolt implements the iCommitter interface. So this just says this bolt must participate this bolt is a committer. And all that means is that finished batch method is strongly ordered on commits. Right? So we're going to make sure that we don't commit batch 2 until we know batch 1 has been committed. Let me finish it. Okay, so the way this works is that the way finished batch works, so it's called during the commit phase. So what it does is it gets the current value out of the database. And then rather than store just the count in the database, what you do is you store the count and the latest transaction ID associated with updating that count. Right? So you store not just the count, but actually a pair of values. And the way this works is that rather than just blindly update the count, you only update the count if the transaction ID in the database is different than the transaction ID of this batch. Right? So if they're different, you go ahead and you increment the count. If they're the same, you do nothing. So let's think about why this works, right? So let's say you have 6 tasks in this idempotent counting bolt, right? Let's say you go to commit a batch, and let's say 3 of them succeed, so they update the database, and 3 of them fail, and they don't update the database. So what you'll do is you'll go ahead and retry the batch, you'll recommit, and then the ones that succeeded before, well, they'll see, oh, this transaction ID is already in the database. I've clearly already done this processing before. I can skip. I just won't do anything because I know that my partial count is already represented in that count. Now the other bolts, they see, oh, the transaction ID is different. My partial count is not represented in the database. I'll go ahead and update it. Right? And the reason this works is because of the strong ordering of commits, that those transaction IDs are done in order. Does that make sense to everyone? Yes? Okay. Go ahead. You're saying what happens if there's like a problem and it just can't execute? That's there's nothing Storm can do in that case. So that's really just a problem with your application. So you have to make sure your application is robust enough so it works for any input. So I didn't come up with this idea of storing the transaction D in the database. It's a great idea, but I just want to give a shout out to the Apache Kafka devs. They came up with this trick of storing the transaction D in the database. It's a really clever trick, and I think Storm takes this idea to its logical conclusion. So one cool thing about transactional topologies is that even though the commits have to be ordered, you can still process multiple batches in parallel. So like while you're committing batch 1, you can still be computing the partial counts for batches 2 through 10. What this does is this is basically like pipelining, and it lets you get optimal resource usage of your cluster. So one note about transactional topologies, they require a more sophisticated input source than something like Kestrel or RabbitMQ. But it turns out that Kafka has the perfect semantics for transactional topologies. And if you look in the Storm Contrib project, it has a transactional Spout implementation for Kafka. Okay, so now I want to go over a few examples of how you might use Storm. So the first example I want to show is you might use Storm to implement a crawler, right? So just crawl like HTML pages and store them into a database. And the topology for a crawler would be really simple. You would have a spout, which just emits URLs to crawl, and you'd implement your scheduling logic in that spout. And then you'd have a bolt, which just goes ahead and fetches that content from the web. And then you might have another bolt, which writes that into a database, right? And if you want to parallelize the fetching, you just tweak the parallelism of your bolts. Right, so this is a really straightforward example. So another example is something we use Storm for at Twitter. So we have a product called Twitter Web Analytics. So here we show, or one of the things this does is it shows a graph of number of clicks over time to URLs that are being tweeted. Right, so advertisers use this product very heavily to understand how their tweets are performing. So this topology is a little bit more involved. So on the left, we have this clickstream spout. So it emits a stream of all the clicks happening on Twitter. The way we actually get that data is for those of you who use Twitter, you'll notice that every tweet is wrapped in this t.co shortener. And so that just lets us know whenever clicks happen on Twitter. So we get the clickstream. And then we have a bolt, so the clickstream just contains the short URL, but we need to know the actual resolved URL to do the statistics. So we have a bolt called the URL resolution bolt, which just maps a short URL to a long URL. And then we have a bolt which does bot filtering. So obviously advertisers don't care for bot clicks; they just want to know about actual humans clicking. So we do some filtering. And then with that filtered and resolved stream, we first of all append it into Hadoop so we can do offline batch processing. Then we update statistics in Cassandra. And then we have another pair of bolts which will actually compute what are the top user agent refer combinations that are being that are coming from that are clicking on URLs. This is useful for us to see, okay, there's clearly this other bot that we're not filtering that we should be filtering. And doing that top user agent's computation actually requires a two-stage computation, which is why there are two bolts there. So another interesting example, something we actually have been doing recently with Storm, is using Storm as a database, or as a database-like thing. So the idea is that to assist in some of our ad targeting, we want to know what are the last 10 clicks a user has clicked on. What are the last 10 URLs a user has clicked on? And we don't even care for this to even be reliable. If we lose the data, it's not a big deal. We just need to be able to get it very, very, very quickly. So it always needs to be stored in memory. So you can actually implement this on Storm with a topology like this. So first we have the clickstream spout, so the same clickstream I described. And that goes into a bolt, which partitions the stream by the user ID and then keeps in memory the last 10 clicks for that user, just in memory. And then if we actually want to query it, what you do is you hook this into DRPC. So you have a DRPC spout, which emits function notifications, where the function is basically get me the last 10 clicks for this user. So that partitions that request stream also by the user ID. So that makes sure that the requests get routed to the task with the right information. And then whenever a request comes in, it sends the the results to that return results bolt, and that'll send it back to the DRPC server and back to the client. So it's kind of an interesting usage of Storm. Okay, so just a few more tidbits about Storm. Storm has a UI, which is similar to the Hadoop UI. So this just shows you like what topologies are running on your cluster, and then gives you detailed statistics about those topologies. So it'll tell you like for every Spout tuple, what's the average latency until the whole tuple tree has been completed. And then for every bolt, it tells you the average processing latency there. And through every component, it tells you the throughput through that Spout or bolt. Storm has a companion project called Storm Deploy. So this is a one-click deploy tool for launching Storm clusters on AWS. It's a really cool project. It's pretty easy to use and helps you get up and running really quickly. All the code I've shown in this presentation are in the Storm Starter project. And that just contains some example topologies that you can run locally and just play around with to learn the basics of Storm. Storm also has a lot of documentation on the wiki. Has more than 20,000 words of documentation. I think it's pretty good. I've gotten a lot of good feedback about it, and it should help you learn Storm and get it running. All right, and finally, Storm has a growing ecosystem of third-party tools to use with Storm. So there are Scala, JRuby, and Clojure DSLs available. I wrote the Clojure DSL, and members of the community wrote the Scala and JRuby ones. There's a whole just plethora of Spout adapters, so Kestrel, Redis, AMQP, JMS, and you name it, there's probably a Spout implementation for you. People have written multi-lang adapters to use Storm with other languages. Like Storm comes with adapters for Ruby and Python, and people have written JavaScript, Perl, I think PHP, and other language adapters. Right, and then there's some bolts that people have open sourced just to automate certain workloads of updating things like Cassandra or MongoDB. All right, can I take any questions?
What's the largest Storm cluster? Probably Twitter.
Yeah, oddly, we actually aren't the biggest user of it. So I know I did a survey a few months ago, so I probably should do that survey again. But I know there's a few people using it to process 1 million messages per second. I don't know how big their cluster is, but we've tested it up to like 30 nodes, and works fine. I mean, it should scale much higher, but we haven't really done those tests. 30 nodes can process a lot of messages per second.
It's sort of surprising in creating topologies, you specified the number of instances of a bolt. Is there a way to say it should be dynamically sized based on load?
Yeah, it's a good question. So the way Storm works is that topologies are actually static once you deploy them, so you can't like change a topology while it's running. It turns out that implementing that would actually be very complex. So Storm opts for simplicity, especially if there's an alternate solution. So if you want to like change a topology, the way you have to do it now is you have to kill the topology and redeploy the new one. So it's pretty easy to do, although it does require you to take like a minute or two of downtime. There is a planned feature called swapping, where the idea is that you could take a running topology and then swap it with this new topology you want to run. So your new topology could just be the same topology, but with the parallelism tweaked, maybe a new bolt added or whatever. And the way that would work is it would actually launch the new topology in a deactivated mode, so it wouldn't be like doing any processing. And then once it's launched and the processes are prepared and all that stuff, it would deactivate the first topology, so stop sending it messages, and then activate the new one, and then tear down the first one. So that would let you do everything you want in terms of scaling, and also would just let you completely modify the topology and also minimize downtime. So that's the plan for that kind of like topology evolution.
Speaking of plan, any comments on the roadmap for Storm? Is there any support from Twitter? Do they have any particular directive or ambition to
Yeah.
make it supportable for enterprises specifically, since
Enterprise, you mean like consulting, support or something like that?
I mean,
Yeah.
when enterprises make decisions whether or not to adopt things, sometimes
Yeah.
they love it, but can't do it because it's not supported or it's not,
Yeah. I mean, it's an open source project, so
Right.
yeah. So you'll find, I mean, the community is really this community for Storm is like really good and it's pretty big already, and it's getting bigger every day. So support comes from the community, and I spend a lot of time answering questions on mailing lists. There's no like professional support for Storm or anything. Storm's, again, is a pretty young project. It's only like, 7 months old. So in terms of just like roadmap for the project, there's no like official roadmap, but I can say that like some of the things coming very soon are kind of enhancements on the scheduler. So right now, the way Storm decides like which machines workers run on and which machines tasks run on is basically arbitrary. And Storm basically just tries to spread the workers evenly across the cluster and then spread the tasks evenly across the workers. But it turns out for a lot of applications, you need more control over that. So you might need to say, these tasks can only run on these machines because they have the resources it needs, right? And so Storm, one thing that I almost have ready is integration with Mesos. So I don't know if any of you guys know what Mesos is. Mesos is this cluster resource manager. So it'll let you do things like have, like run multiple topologies on a cluster and have true resource isolation between the topologies. So like if one topology starts using a bunch of CPU, it won't affect like the other one running on the same machine. So that's gonna be really cool, and that'll let you do things like say, this topology needs this much memory for its tasks, but this other topology needs less memory. And then we're also working on a pluggable scheduler, so you can actually implement your own code or plug in your own code to say where tasks should be running and things like that. Yeah.
Hadoop has a notion of partial success, right? So
Yeah.
you can accumulate errors and stuff like that. Is there an equivalent in Storm?
Yeah, so there's kind of two aspects to that. So the first is, so with kind of like the vanilla Storm stuff, like streams, spouts, and bolts and stuff, so you track each tuple individually, right? So if any part of processing that tuple tree fails, you replay from the source, right? But different, like you could have one tuple fail and another one succeed, and then only that one tuple that failed will be replayed, right? So in general, like the processing of an individual tuple is cheap, so it's fine that you have to replay it from scratch. Now with things like DRPC and transactional topologies, you process like batches, right? So that's now it's getting more similar to Hadoop. So you might wonder, okay, does it, like if you have a partial batch failure, do you only replay that partial batch like Hadoop does?
Or just ignore that partial batch failure. At some point, maybe you only get 98% result.
Well, even in Hadoop, if it keeps failing, the job is still considered a failure.
Yes, it's considered failure, but you'll get a partial result.
I see what you're saying. Yeah, Storm doesn't have any notion of that. You have to make sure your application handles all the possible inputs. Yeah. Go ahead.
In terms of monitoring and connected to that same question, if a tuple or a batch has to be replaced, is there monitoring or mechanisms by which you get to say how many times it gets replayed before it gets dumped somewhere else?
Yeah. So there is no, so Storm itself doesn't monitor that. Potentially you could have that monitored on your actual source. So like potentially you could enhance Kestrel, for example, to tell you how many times it played a message. There's no way for Storm to really know how that works. Although Storm does have, so besides like the basic UI that Storm has hooks where you can put in your own code, like into like the various lifecycle events, and that could help you plug in like your own monitoring or like custom tracking.
Could you track that in the Spout? How many times you replay the message ID?
So the way the actual replay works is it's up to the source of the spout. So like the way Kestrel Spout works, for example, is that when it takes a message off the Kestrel queue, so Kestrel provides it with the ID of that message. Kestrel is kind of like RabbitMQ. And then the idea is that, so now it holds that ID in memory, and then if the tuple tree gets completed, it goes ahead and sends an ACK message to Kestrel. If it doesn't get completed, or if it fails, it sends a fail message. So the burden is on Kestrel to do the actual replay. So Storm will, so like let's say it fails, so Storm will just get a message from Kestrel and it will happen to be the same one, but Storm doesn't track whether it's seen that before. That's why I was saying that you'd probably implement that in your source queue.
Do you have forms of back pressure in the system for the bolts and spouts?
Yeah, it's a good question. So yeah, you definitely want to avoid situations where your consumers are slower than your producers, because that ends up with what's called queue explosion, where you run out of memory or whatever, your buffers get too big. So the way you actually handle this in Storm, it's actually really simple. There's a property in the config called topology max spout pending. So that indicates the maximum number of tuples that can be pending, like not fully processed yet. So you might set that to like 10,000. So that limits the total number of tuples that can be active, and that prevents any sort of queue explosion.
So you basically back up to the spout.
Correct.
You're like, all right.
Throttle on the spout, and that protects the whole topology. Yeah. Any other questions?
Did you have to do any special zero to three tuning for internal storage?
Yeah. So Storm uses this library called ZeroMQ for passing messages between tasks. And actually, the total amount of code using ZeroMQ is like 50 lines. It was really simple and was like, just worked.
So yeah. No tuning, just get the library.
Just use it and that's it. Yeah.
All the possible parts, like pops up, pops out.
Yeah. Yeah. It just uses push-pull sockets, and if there's any failures, it just will it'll just connect to a different machine.
So it actually uses one topology.
Sorry, it uses what?
It uses 1 0 2 topology. It doesn't use pops out.
Yeah, it just uses push-pull sockets. Yeah. It was really straightforward. Yeah. Any other questions? Okay, thank you guys very much.